So it's time to start our final session of this conference. So the first speaker is Nikita Sopenko, and he will talk about a many-body index for 2D chiral or superconductors.
Thank you. Thank you very much for the opportunity to speak here. My talk is based on these two works and some work in progress. And actually, I remember that I came up with some ideas for this work while I was attending a summer school sister algebraic quantum mechanics that was organized by Markus. So I'm very glad that I can come back to Boulder and talk about this. It was a great school, and I hope it was not the last one. So I'll start with some general motivation. So motivation is to understand classification of gapped phases of matter at zero temperature. So quantum body system is called gapped if the excited states are separated from the ground state by some energy gap in the thermodynamic limit. And by definition, two systems are in the same gapped phase, and there is a continuous way of deforming one system into another without closing the gap and while preserving our curve. And schematically, we can say that gapped phases correspond to connected components in the space of all Hamiltonians, gapped Hamiltonians, and this picture can schematically represent this space. And of course, there are different flavors of the game. We can consider Hamiltonians with ground states that preserve some symmetry, for example, charge conservation or time reversal. But in this talk, I will be mostly focused on systems without any symmetries at all. So in order to understand some general principle how to classify such phases, we need some model that is mathematically tractable but also sufficiently generic. And one of such models is just to consider some lattice system in Euclidean space. And with size of this lattice system, we have associated Maranomodes that satisfy this commutation relation. So they generate some algebra for durables. You can think of it as some infinite dimensional Clifford algebra. And the system is characterized by a Hamiltonian, which is a sum of local chirps. So it is even in these Maranomodes and has some coefficients which depend on sites and decay rapidly with the distance between the sites. So they kind of describe interaction between the Maranomodes. So what is known about this problem? So one of the milestones in the field was the classification of free systems that corresponds to just Hamiltonians which are quadratic in Maranomodes. And such systems are fully characterized by this numbers ajk, which you can think of as like forming some matrix or like some operator in the dimensional Hilbert space, satisfying certain properties. So it is real, it is symmetric, and also this matrix coefficients, they decay sufficiently rapidly with the distance between the signs. And such problem was solved to gapped systems. So we now know the groups which classify all the spaces in different dimensions. So elements of this group correspond to different phases. And in fact, we know how to classify them with various symmetry types. They organize very nicely into this periodic table. But we'll be mostly focused on what's called plus D topological superconductors. So these are systems which do not have any symmetries at all. And just to give you some idea how these pages are, how to actually extract some topological invariant out of the phase, we'll consider two-dimensional free-fermionic systems. So we have some two-dimensional lattice with some Hamiltonian like this. And the ground state of such systems is fully characterized in terms of the two-point function. So just the expectation value of two Maranomodes, which can also be organized into some operator acting on this one-particle Hilbert space, which is orthogonal projector satisfying some additional symmetry. So somehow information about this phase is fully encoded in this projector, and there should be a way of extracting the number that classifies these phases, so they're classified by z, and you want to define some z-valued number out of this projector. And there is a very complete procedure to do this. So we consider a lattice system and split it into three regions, like in this picture, and we define a certain numbers which depend on three sides, and depend on this projector is defined by this formula. And once we have this set of numbers, we consider a certain sum over all sides which belong to different regions corresponding to this free partition. An important point is that this sum is convergent. So these terms, they actually decay rapidly if some of the sides are far from each other. And the main contribution into the sum comes from sides which are localized near this triple point. So it's some kind of finite contribution, and that's why this number is actually finite. So it's some a priori real number that is defined in terms of this projector. And the point is that this number is actually quantized. So one can prove its quantization. And moreover, it has a physical meaning. So if you have a material with a boundary, then the boundary modes of this material they're gapless, and they can have different chirality. They can be either left moving or right moving, and this number just counts the difference between this left and right disorders. Also, I want to emphasize that this number is defined for systems without any translation symmetry, which is kind of physically relevant because we also want to model systems with disorders. So we don't want to assume any translation symmetries at all. And this number is actually complete invariant. So one can prove that if two systems have this same number, then they're actually related by some deformation, preserving data. In high dimensions, there are like similar invariant can construct it using similar math. So,
So I mean, so Chern number and the continuum, well, even a lot is divided in terms of some very curvature.
yeah, if you have translation invariance, like for brilliant zone, but the point is that it is defined even if you don't have any translation C, but it coincides with translation invariant case, especially.
You mean like you have disorder or something?
Yeah. So people kind of develop this formalism to also address systems with like
This idea of breaking under three regions and construction.
Yeah.
Yeah, and this is it's like bulk fertile hot.
Yeah, that's I will talk about this in a moment. So, but we really want to understand interacting systems. So we want to understand what happens if you now add arbitrary interactions. And of course, like all this formalism with two-point function, it breaks down. And in general, it's a very difficult problem. So we cannot solve it in full granularity in any dimension. So we can analyze it case by case. And the simplest case is one dimension. And in one dimension, we have very well understanding how to classify such phases. And if you don't have any symmetries, then actually they just classified also by the two, like in the free-fermionic case. So there are two different phases. Both of them can be represented by free fermions. So this is just quadratic Hamiltonians. So we have a chain of Maranimals in one dimension, and we have different way of pairing these Maranimals. In those two different ways correspond to different phases. And now we know how to prove that actually, even if you turn on arbitrary interaction that preserves the gap, we cannot deform one state into another. But in two dimensions, the problem is already way more interesting. So in two dimensions, first of all, there are a lot of phases which cannot be represented by free fermions. So they're genuinely interacting phases. So we don't know how to classify them, but we do have some reasonable guess by physicists. So and basically this reasonable guess says that they're classified by two pieces of data. So the first piece of data, it characterizes topological excitations in the system. So the system have interesting phenomena. They have fractional topological excitations called anyons. And there is some mathematical structure that describes these anyons called modular tensor category. So we know many examples, exactly solvable examples, chiralize different models, different modular tensor categories. But we don't know how to prove it in general, like any gap state, you can extract this modular tensor category out. And the second piece of data corresponds to anomalous transfer properties, such as electric Hall conductivity and thermal Hall conductivity that I'm going to talk about in a moment. So we also have examples of phases which only have this anomalous transfer properties. And in this talk, I will do focused on this second piece of data. And for simplicity, consider these models which don't have any anyons. So they have a trivial first piece of data, but not trivial second piece of data. But we don't assume any symmetry. So that's why we call such system topological superconductor. And the conjecture and by physicists that the spaces are classified by integers in the same way as free fermions. So that there is some integers that you can define for any interacting invertible phase, and when this phase, when the system is free, it coincides with this Chern number. So why do we believe that this is true? So first of all, if you consider systems with U1 symmetry, then yes.
So does this mean that everything with the same Chern number is in the same phase?
Yes.
Oh, okay. So
yes.
okay.
So first of all, when we have U1 symmetry, then there is some topological invariant that we can define for arbitrary gap system with this symmetry, which is electric Hall conductivity. So it has a rigorous mathematical definition. There is a very robust physical argument, Lawson's argument, why this number is actually invariant of the phase. And there is now mathematical proof that this is actually the case. So that is quantized. It's culminated in the paper by Hastings and Michailakis. And in this, when we have this U1 symmetry, this Chern number can be related to this whole conductivity. But we want to address the problem when we don't have any U1 symmetry. So in this case, we don't have this kind of robust Laughlin argument for quantization of like quantization for electric field. But there is some quantum field theoretic argument. So under some favorable circumstances at long distances, our system can be effectively described by field theory. And in this field theory, we have extra symmetry, very big group of symmetries. So if you consider H mode, we have this Virasoro symmetry that is characterized by parallel central charge. And in field theory, this is a robust quantity because it's related to gravitational anomaly. But the problem is that this kind of assumption that we can describe something by field theory at large distances, it's not clear when it is true, why it is true. So we don't have the Virasoro symmetry at microscopic level. So the question is, can we address it directly at the macroscopic level? But there is something from field theory that actually one can try to formalize in the lattice, and that is thermal Hall effect. So if you consider this edge modes at very low temperature, then conformal field theory predicts that there is some energy column that flows through along this edge. And since energy is something that is supposed to be defined even when we break all special symmetries, probably there is a way to kind of formalize this thermal Hall properties on the lattice.
Yeah, just item, bullet 1. Why is it just invertible phase? I think that doesn't it apply for fractional?
Yeah, it also applies for fractional. Yes. So indeed, people trying to define this thermal Hall conductivity microscopically. So there was an attempt by Kitaev and later by Kapustin and Spodinetsa. But the problem with this approach is it's very hard to prove mathematically that, some assumptions that are needed to define this invariant. And it requires some assumption about the absence of phase transition at finite temperatures. So people at the moment don't have any ideas how to prove this. But moreover, it's also kind of not satisfactory because we define some property of a ground state in terms of systems at finite temperature. So it's not, one wants some direct way of just looking at the ground state and defining this invariant. And there was even some conjectural formula that was proposed recently, how to extract this chiral central charge, but unfortunately, it doesn't provide a topological invariant, so there are some counterexamples which violate this formula. So in any case, in any of these approaches, it's not clear, like using thermal properties or some entanglement, it's not clear why the C- should be quantized. Because in the case of U1, this quantization somehow comes from quantization of charge. But here we don't have charge when it gets studied from something quantum. So our goal is to construct some microscopic topological invariant for these interacting systems. And I'll explain a main idea how to do this. So first, we'll make the following key observation. So if you consider just arbitrary interacting system, just a single layer, then it doesn't have much symmetry. So the only symmetry that we have is fermionic parity that changes signs of Majorana modes. But if you take n copies of the system, then it actually does have an interesting group of symmetries. This is a hyperoctahedral group, and it is generated by just permutations of these different layers and fermionic parities of each copy. So this hyperoctahedral group, Bn, it is also can be described as a group of symmetries of n-dimensional cube. And elements of this group can be labeled by permutations with some signs. So some permutation with some extra minus signs, which correspond to the fermionic parity. And the main idea to define this invariant is to consider defects for the symmetry and somehow analyze their statistics. So how to construct defects? So first, for convenience, I'll just choose n to be even. You can also do things with odd, but just for convenience. So we consider a specific element of this hyperoctahedral group that generates a cyclic permutation with extra minus sign. So we can fermute the copies and also apply fermionic parity in the last layer. And it generates Z mod 2n subgroup of this hyperoctahedral symmetry group. And I want to consider the subgroup. So now let's take n layers of my material. Yes?
So these layers are connected or?
No, so they just completely just stand apart.
So nothing here it will be stable against connecting this?
Yes, but we want to construct the invariance of a single layer. So we consider this n layers on a plane, and we try to apply the symmetry only to half plane. So we just permute the sides and apply fermionic parity only to Marana modes in this half. And since the global state is invariant under this symmetry, so it's not going to change our state far away from this boundary, but it's going to modify it somehow here the boundary. So and what we want to do is somehow truncate this modification. So we want to construct a state that looks like this. So we want to kind of apply this modification only near this half line, and 3D picture or the state would look like this. So it's going to be like an n-sheeted branched cover. So there is some cut. And so we have this unsheeted branch cover covering the plane with some singularity at the origin. So it's like a conical singularity. And we'll call such state twist defects, and they're also known as genomes in physics literature. So in what we want to do to define this invariant, we want to consider some exchange process of this twist defect. So we want to create a pair of such defects, and then we want to somehow move them in a special way that kind of cancels all non-universal Berry phases, and define some phase that you get in this exchange process. Yes?
Can you just say a couple of words why this idea of considering many layers and considering these twist defects had a chance to be the right thing? Like what's the...
Yeah, I'll try on the next slide. Yeah, I'll try on the next slide.
Okay, you will. Okay.
Yeah. So the reason why we believe that this procedure works is again, there is an argument from field theory. So if you consider conformal field theory, then there are some special operators that you can define for n copies, which are called twist field operators. And if you exchange these twist field operators in conformal field theory, you get some phase that depend on this chiral central charge. And so the idea kind of why there is some kind of relation between gravitational anomaly and this phase, because like when we apply this, so we construct this twist defect, we can construct it in conformal field theory using some conformal transformation. And this conformal transformation generates some stress energy tensor because of kind of gravitational anomaly. And so that's why there is some kind of interaction between kind of gravity and this statistics of this twist defects. And one can compute this phase in this conformal field theory. So there is a precise formula like this. The point is that since statistics is something that kind of supposed to be, depends only on locality, even if we break all this conformal symmetry, this phase still should be the same. So that's kind of the main point. So this kind of statement of statistics should not depend on any special symmetries, like the statistics of anyons does not depend even if we have disorder. And the special property of invertibility of these phases gives a mathematical way to actually realize this procedure. So there is some concrete procedures that realizes this process, exchange process. So you can construct some unitary operators acting on this lattice system, which provide this phase, expectation value of this unitary operators give this phase. And one can show that this phase does not depend on any ambiguities in the way how we construct this twist defect, because there are a lot of local ambiguities. We can just modify this twist defect state locally, and a priori it's not clear why it should be the same, but the process is designed in a way that it provides an invariant. However, there is some extra global ambiguity, which is important, and this ambiguity is related to the fact that we can always add some z mod n charge on top of this twist defect. So these twist defects may have different z mod n charges, and when we exchange them, then the phase that you get, it depends on this charge, and only theta to the power 2n is a well-defined invariant a priori. So we want to somehow resolve this global ambiguity. So another way of understanding this ambiguity is the following. So if we have twist defect, then there is a way to map it to some rotational invariant state. And this z mod 2n charge then corresponds to just angular momentum of the state. So this ambiguity can be, you can say that this is ambiguity in the choice of angular momentum at the origin for this rotational seat. And in order to fix this ambiguity, we need some additional ingredient, which is reflection positivity. So what is reflection positivity? So it's some very strict property of a state. So if you have some quantum many-body system that has such that lattice is invariant under reflections, you can consider some set of states such that for any operator that acts in one half space, and its reflection in this complex conjugation, this expectation value of this product is positive. So it's some strong condition on the state, and the reason why people kind of even introduce this condition, because it kind of one of the necessary conditions so that our lattice system has relativistic symmetry. So it's a very strong condition because in general, of course, we don't have relativistic symmetry. However, what one can prove is that even though like generic invertible state does not have this reflection positivity property, it always has a representative that does have this property. So there is a some state that has this reflection positivity property and invariant under rotations. In another theorem that one can prove from this reflection positivity is that only states with a specific angular momentum can be reflection positive. So this reflection positivity somehow allows us to fix this ambiguity in angular momentum. So it's some structural property. One needs, of course, to prove this property, but once it's proved, we get this fixing of the space. So that's a kind of main theorem. So the space factors, I explained kind of the idea. I didn't explain the mathematical construction, but there is some mathematical construction of this number. It defines some topological invariant of the phase. And now if you consider this free-fermionic systems, we can compute this phase explicitly. So we can compute it and relate it to Chern number. And we get this formula that we expect from conformal field theory. So this number nu was not, like it was defined only for free systems, but now this number thetas, they defined for interacting systems. That means that since they're all different for different nus, means that we prove stability of this Chern number even if we add arbitrary interaction.
How is this theta n defined again?
Sorry.
How is theta n defined?
State n?
This number, theta n.
Theta n, it is defined as a phase factor that you get in the exchange process of two Twist defects.
Statistical phase.
Yeah, statistical phase. So it's topological spin of this defect, but it's not really annual. But once you gauge this kind of permutation symmetry, it becomes an annual. Okay, so let me summarize. So the states, free-fermionic states with non-trivial Chern number, they provide examples of non-trivial 2D phases of matter. So now we have a mathematical proof of this. So the essential ingredient in constructing this invariant is this observation that n copies have this extra permutation symmetry, and also reflection positivity that further fixes action of permutation symmetry, the defects for this permutation symmetry. And this, well, I can say that gives microscopic characterization of the chiral central charge. So when our system can be related to conformal field theory, we get the same numbers that are related to chiral system. So there are various open questions. So I said that the conjecture is that this invariant is actually complete. So we don't know how to prove it at the moment. So we don't know whether all the phases are represented by the free-fermionic invertible phases. So also this kind of way of defining it is not clear at all how it is related to servo Hall conductivity, though it is believed that there should be a relation. And furthermore, yeah, well, this construction mathematically it is defined only for this invertible phases, but I expect that the same idea can be applied to gap states. It's just harder to prove mathematically that this twist defects, that you can produce gap twist defects, and also that they are mobile, that you can actually move it for arbitrary gap states. But probably it can be done in the near future. Okay, I guess I'll stop here. And happy birthday, Markus. Thank you.
Yes, thank you for this nice lecture. Are there more questions on what we had?
What is any relation? So this n copies thing feels kind of like people take n copies and they're treating Renyi entropes. I don't know. Is this just like a passing similarity or?
Yeah, I don't know. I don't know.
I missed the connection to the chiral central charge. I mean, it's the theta you define is the exchange angle, the angular momentum.
Yeah.
Or spin. But how is it related to the chiral central charge?
So in conformal field theory.
Oh, I see. There's
Yeah.
okay. in CFT, that nu is C in the C.
Yes.
I see.
Or just your construction makes sense. It was on a URL basis.
Yeah, so everything, yeah, actually, yeah, I already wrote a paper about bosonic case. So yeah, everything can be done in the bosonic case, and furthermore, you can prove some quantization condition of this theta. So there is some 16, multiple of 16 difference between bosonic and fermionic case, and it can be proven that it also appears in the definition of this invariance.
So the value of theta can be predicted, so the central charge, or a.
So I don't know how to prove that for any phase, this theta has this form for any gap state. So for free fermions, I can explicitly compute it and confirm this form.
And C in that case will be.
Just Chern, yeah, half of the Chern.
And can you map these into split systems, and what will they be related to any? At least the representatives will be related to any classical models.
So you mean spin systems? You mean without fermions, the bosonic spin systems?
No, so we map the fermionic degrees into spin degrees and just work at spin systems.
Well, we can consider like even sector of this fermionic system. So we can embed the spin systems into fermionic systems. And then, yeah, we can also define this invariance.
And when you go into split systems, do you get any classical models?
Not that I'm aware of. So everything seems quantum.
So creating this twist defect, that you're confident that you don't close the gap, like
Yeah, so
it's a local object.
right. So the thing is, for invertible phases, one can actually prove that you can create this spin defect, twist defect, just by quantum circuit localized along this cut. In this quantum circuit, it preserves this gap.
Okay. It's time to thank speaker again.